So in this lecture I will explain the efficiency of single phase transformer. So the percentage efficiency is equal to output power by input power into 100. So input power can be expressed as output power plus losses in a transformer. There are two major losses in a transformer. One is variable losses or copper losses, and another one is iron loss or core loss or magnetic loss. The iron loss can be divided as hysteresis loss and eddy current losses. Our input power is required to meet the losses and to produce the useful output power. Generally, the transformer rating is in kVA. The transformer rating is in kVA. The transformer rating is in kVA. So output power is equal to kVA into cos phi 2. So if you substitute here percentage efficiency, output power divided by output power plus losses, in that we are having two major losses, iron losses plus copper losses, full load copper losses, and kVA into cos phi 2 divided by kVA cos phi 2 plus iron losses plus copper losses multiplied with 100. So we can write it like this also: E2I2 cos phi 2 divided by E2I2 cos phi 2 plus iron losses plus I2 square times of R02. This is the total full load copper losses when referred to secondary. I will give an example. If the full load current is 10 ampere and the half load current is 5 amperes and 3/4 load, the current is 3/4 into 10, that should be equal to 7.5 amperes. As load changes, load current is also changes. It's either increase or decrease. If a load decreases, I2 decreases. If load increases, I2 is also increases. So for that, whatever this fraction is there, I will put it as x. Then efficiency at x fraction of load is equal to x E2 I2 cos phi 2. Wherever I2 is there, put x I2. So x times of E2 I2 cos phi 2 plus iron losses. So this is xi2 whole square, that means x square I2 square. So x square I2 square into R02 multiplied with 100. Then you will get the percentage efficiency at any fraction of load. And this can be written as, where E2 I2 is kVA of single phase transformer, and x times of kVA cos phi 2 divided by x times of kVA cos phi 2 plus iron losses plus x square times of I2 square into R02. So this is a percentage efficiency at any fraction of load. The transformer rating is in kVA. Why? Because the iron losses are depends on voltage and the copper losses are depends on current. The losses are not depends on the power factor. The losses depends on the voltage and current. The temperature rise in any machine is due to the losses. There are two losses are there. One is iron loss and copper losses. Iron loss is directly proportional to voltage. Copper loss is directly proportional to current. The product of these two will give the volt ampere rating. So in order to get the maximum efficiency of single phase transformer, maximum efficiency of single phase transformer, and differentiate this equation with respect to variable. What is the variable in this part? Power factor and as well as the load current. Differentiate this equation with respect to I2 and made equal to 0, then you will get the maximum efficiency of single phase transformer. So by using a U by V method, X times of E2 I2 cos phi 2 plus iron losses plus X square times of I2 square R naught 2 into derivation of X E2 I2 cos phi 2 is X E2 cos phi 2 minus U, V into U dash minus U into V dash X E2 I2 cos phi 2 into derivation of this will be X E2 cos phi 2 plus iron losses differentiation is 0 plus X square 2X square I2 R naught 2 is equal to 0. So from this X E2 cos phi 2 you will take it as a common, and that is not equal to 0. Then X E2 I2 cos phi 2 plus iron losses plus X square I2 square R naught 2 minus, see here I2 is there, X E2 I2 cos phi 2, only I2 is pending here, and multiplied with I2 inside X E2 I2 cos phi 2 plus 2X square I2 square R naught 2. This is minus, should be equal to 0, and these two are cancelled. From this X square I2 square R naught 2 is equal to iron losses. This is the condition for maximum efficiency. Here at what fraction of load, at a fraction of load maximum efficiency takes place. Under root of iron losses by full load copper losses. Iron loss divided by full load copper loss. At KVA corresponding to maximum efficiency is X times of KVA, where X is equal to under root of iron losses by full load copper losses. Full load copper losses. See, copper loss at full load is 1600 watts, and the copper loss at half load is how much? We know that copper loss is directly proportional to I2 square and WCU1 divided by WCU2, or in this PCU and WCU both are same. 1 divided by 2 is equal to 1600 watts. I2 square means I full load by 2 whole square, and these two are cancelled. WC1 is 1600 divided by WCU2 is equal to 4, and WCU2 is equal to 1600 divided by 4, that should be equal to 400 watts. It is not 800 watts, it is a 400 watts. The copper losses are reduced to 400 watts if the full load copper loss is 1600 watts. If you draw the characteristics, the percentage efficiency versus load current, this is called the load current, you will get the characteristics is like this. So at this condition, copper loss is equal to iron loss, but after this copper loss is greater than iron loss, below this iron loss is greater than copper loss. So percentage efficiency is equal to x E2 I2 cos phi 2 divided by x E2 I2 cos phi 2 plus iron losses plus x square times of I2 square R naught. As load increases, I2 is also increases, and this term is increases. Okay, and this x value is very small for lower values of load currents, and instead of increasing denominator, the numerator will be increases more. So that's why the efficiency will be slowly increases, and it will increases up to maximum point. After that it will be decreases. So this is the maximum efficiency condition when variable loss is equal to constant losses.